Thank you. I can't repeat all that. Well, welcome back, the few, the proud, and the brave. The rest, well, the rest is gone. So, all right. So let's start by doing our second quantization in the case where sigma 2 is the torus. So sigma 2 we can write as a quotient of R2 times z plus z. And so this is a topological surface, and if we talk about our two coordinates as sigma 1 and sigma 2, we could choose an orientation by saying that d sigma 1, d sigma 2 is the positive volume. Now, in order to do Kähler quantization, we need to introduce extra structure, namely a complex structure. It's not part of the topological theory, and I'll let J be an abstract notation for complex structure. Now, in the case of the torus, it's very explicit. Every torus has a complex manifold, can be written as E tau equals a quotient of C divided by this lattice inside C, and this will be a nice two-dimensional surface as long as the imaginary part of tau is not 0. And then you can say that the complex structure is determined by saying what a 1,0 form is, and d zeta is d sigma 1 plus tau d sigma 2. So that's a nice 1,0 form. When you have a complex structure, you automatically have a natural orientation, I d zeta wedge d zeta bar. And now you just work this out, little exercise. This is m tau d sigma 1 wedge d sigma 2. And so we'll take m tau to be positive, as is standard. Now there's a fact about, let's see, yep, this moves. Okay, there's a fact about complex structures on the torus, which is that E tau is isomorphic to E tau prime as a complex manifold if and only if tau prime is a tau plus b over c tau plus d, where a, b, c, d is in SL2Z. Okay, so then we can talk about the moduli space of complex structures on sigma 2. And in this case, it's just the upper half plane, the upper half tau plane, divided by SL2Z. And so that's often, you can write a fundamental domain for that. It's often chosen as the keyhole region. And so we identify this side with this side, and we have a Z2 identification around here. So there's an orbifold point here of order 2 and order 3 here. And this gives you what's called the moduli stack. So it looks of complex structures. So it looks a little like that. Okay. So that's the space of complex structures in this particular case of the torus. And now a complex structure on the surface, the spatial surface, implies a complex structure on M flat. So remember, M flat was also a torus in this case, because we could write our flat gauge field as A1 d sigma 1 plus A2 d sigma 2, where A1 and A2 are just constants modulo 2 pi. And now we can expand this as A zeta d zeta plus A zeta bar d zeta bar. And now you would use either A zeta or A zeta bar as a holomorphic coordinate on the moduli space of flat gauge fields. Now we're going to choose our holomorphic coordinate z. So this is a holomorphic coordinate on M flat. And we're going to choose that to be proportional to A zeta bar. I'll say why in a moment. So this is to be the proportionality constant is chosen, so it's like this, so that z has periodicities like this, where n1 and n2 are integers. Why A zeta bar? Well, you see, the d bar operator on a Riemann surface under variation of complex structure turns into the d bar plus mu times d. So if you want to change the complex structure on a surface, you shift what you mean by the Cauchy-Riemann operator. This is called a Beltrami differential. And in the theory of complex structures, Beltrami differentials are the holomorphic tangent vectors to the space of complex structures. And so we want to use A zeta bar. All right, so now we seek a holomorphic line bundle. Let's call it L kappa over the moduli space of flat connections with its induced complex structure that I just told you about. So the way we're going to get at this line bundle is we're going to say, okay, so sections, any sections actually, sections of this line bundle must be such that e to the minus scalar potential times psi squared is single valued on sigma 2, where the Kähler potential is fixed by demanding that the symplectic form, the thing that counts numbers of quantum states per unit phase volume in phase space, is I over 2 pi dd bar of k sub kappa on the one hand, but on the other hand, we derived what omega is. It's kappa over 2 pi squared times the integral over sigma 2 of delta A wedge delta A. Okay, now let me stress what this means, that this is single valued. So you see, if you quite generally, if you have some line bundle with a Hermitian metric over some manifold, then you have patches. Okay, and in each patch you would describe a section of the line bundle by some function, psi alpha and psi beta, on the patch. And then on the overlap, you would say that these are related by a transition function. So what's going on here is that e to the minus k in the alpha patch, psi alpha squared, is equal to e to the minus k in the beta patch, psi beta squared. So that means that the Kähler transformation is k alpha equals k beta plus log g alpha beta plus log of g alpha beta bar. Okay, so for a holomorphic line bundle, this would be a holomorphic function on the overlap. Okay, so in Kähler quantization, the answer for our Hilbert space is going to be that with complex structure J, we're going to have the holomorphic sections of this line bundle we're about to construct. I have to amend this formula in just 1 second. Now notice that it depends on J. So we should think of this as a fiber of a vector bundle over the space of complex structures on sigma 2. Okay? And now I'm going to amend this, as I said. We have to tensor by a line bundle. So that's just a one-dimensional vector space on each fiber, so you wouldn't notice if you're just quantizing at a fixed J. You know, if you tensor your vector space by a one-dimensional vector space, it's still the same vector space, right? So you're only going to notice if you start varying the complex structure. And there's there's a line bundle that goes here. I'll say a little more about it later. So this kind of violates what we want in topological field theory, because I had to choose this complex structure to quantize the space, but this is a topological field theory, so it shouldn't depend on a choice of complex structure. It wouldn't be a topological field theory if the Hilbert space really essentially depended on complex structures. The space should only depend on the topology and the orientation. So the point is that there's going to be a projectively flat connection on this, which allows us to identify all the fibers. So there'll be a projectively flat connection which allows an unambiguous identification of a single Hilbert space of states. Okay, so now what we have to do is we have to solve equation star here. So you see, we know this, and if you plug in my formulas over there, you will get tiny little exercise that this is I kappa dz wedge dz bar over m tau. Okay, so we have a differential equation, dd bar of k sub kappa equals this. This is very explicit. And we can solve that differential equation rather easily. So k sub kappa is equal to 2 kappa times a function I'll call k, where k is 2 pi times the imaginary part of z squared over m tau. So if you take dd bar of this quantity, you should get what I'm claiming. Now notice that this is not single valued on the torus, right? Because z is identified with z plus n1 plus n2 tau. So e to the minus k transforms under z goes to z plus a plus b tau, or a and b are integers, to e to the minus k. And I'll write it this way. E sub b of z tau inverse e sub b of z tau complex conjugate inverse. This is again an exercise. This is really straightforward, where you should find, if you do the exercise, you should find that e sub b of z and tau is equal to e to the minus I pi tau b squared minus 2 pi I bz. Okay? That's why we need patches, because this e to the minus k is not single valued. Instead of patches, in this case with the torus, it's actually easier to lift to the universal cover, that's the complex plane, and work z plus z equivariantly. By that I just mean demand that everything transforms properly under z goes to z plus a plus b tau, or a and b are integers. So a is here and b is here. Okay? So now it's useful, before constructing L kappa, it's useful to construct another line bundle. I'll call it the theta line bundle over m flat, which has the property that e to the minus k times its sections, absolute square, are single valued. Okay, so again, we lift to the universal cover. So we lift to the universal cover. And if we want holomorphic sections, then psi of z has to be an entire function on the complex plane. And it also has to be such that this is single valued, but you know how the e to the minus k transforms. So therefore psi of z plus a plus b tau is e sub b of z tau times psi of z. So now we have a little functional equation on an entire function. And I leave it as an easy exercise to show that there's a one-dimensional vector space of solutions to that functional equation. Every solution looks like psi of z equals constant times theta of z. This is the theta 3 of z that she was using. At z equals 0, I think he was using it. So anyway, with z, it looks like this. E to the I pi tau n squared plus 2 pi I n z. So that's a nice little exercise. Solve that functional equation. Okay, so now we can construct our line bundle. L sub theta is a line bundle over E sub tau. So L sub theta is just C times V divided by Z plus Z, where V here is, again, a copy of C, but you think of it as the fundamental representation of U1. That's how you should think of it conceptually. And okay, so I have to tell you how the generators, so let's say there's a generator of G1 of this Z and a G2 of this Z. I have to tell you how the generators act. So G1 takes Z psi, just goes to Z plus 1 psi, and G2 takes Z psi, goes to Z plus tau, E sub B of Z tau times psi. Okay? So now I've told you how z plus z acts on c times v. And so we really have a line bundle. The equivalence class of z psi projects by pi down to the equivalence class of z. Okay, so that's the theta line bundle. So now for us, L sub kappa is just going to be L sub theta to the 2 kappath power. Why 2 kappa? Because we had a factor of, did I write it? I think I wrote it. It's just hiding. Here we are. We have a factor of 2 kappa times k. Okay, so that's the 2 kappath power. So the holomorphic sections lift to entire functions on the z-plane, which now satisfy this functional equation. Okay, so now you have this functional equation, and you want to solve that. And there is there's a 2 kappa dimensional space of solutions. And there's a natural basis called the level k, level kappa, theta functions. So I'm going to generalize those theta functions. So I want to write it in a way that I don't erase it. Okay. If I start to erase this, holler. Okay. Say, don't do that. Okay, so theta of mu kappa of z and tau is the sum over s in the integers of the exponential of 2 pi I kappa tau s plus mu over 2 kappa squared plus 4 pi I kappa z s plus mu over 2 kappa. All right, and you notice if you shift mu is an integer, if you shift mu by 2 kappa times an integer, then you can undo that by shifting s. And so so theta of mu kappa is the same thing as mu prime kappa if mu and mu prime is a multiple. If mu prime minus mu is a multiple of 2 kappa. Okay, so that's how we solve that. And so now, finally, what are the quantum states? So a basis of quantum states for our quantization of our torus with complex structure J is psi of mu and kappa of z and tau is theta of mu and kappa of z and tau divided by eta of tau. Okay, now why the division by eta of tau? Well, I'm not going to derive it because I got a lot of other things to do, but you can derive this by normalizing the wave functions. If you go back to the original wave functions and you want to make some normalization condition like this, where we're really integrating over A mod G, then that normalization will force you to put a 1 over eta of tau here. The essential fact that you use is that if you look at the determinant prime of the positive Laplacian, which is basically the determinant of d bar, then this turns out to be, well, this is exactly m tau times eta of tau to the 4th power. That's the essential mathematical fact. Okay, and that's why there's this extra line bundle over here. And what's the parallel transport? Well, you can work out for yourself. You see, there's 2 powers of s here and 1 power of here. So therefore, these theta functions satisfy a heat equation, right? If you take 2 powers of z two derivatives with respect to z, you can compensate that with one derivative with respect to tau. And so the exact statement is that d tau plus I over 8 pi kappa d by dz squared on psi equals 0, where d tau is a proper covariant derivative on the upper half plane, holomorphic. And I won't have time to explain this, but this is all very closely related to rational conformal field theory. So this here, these are the conformal blocks of a theory R squared of a two-dimensional conformal field theory, d phi, d bar phi, where phi is identified with phi plus 2 pi, and R squared, the radius of the circle it's mapping to, is a ratio of integers such that the product of the integers is kappa. Okay, so if you work out, so she was talking about the conformal blocks of the 4-point function. But in rational conformal field theory, all the correlators are expressed as sums of holomorphic times anti-holomorphic functions. Those functions are called conformal blocks. So in particular, if you wrote down the partition function of the rational torus, it would be something like a sum of psi mu kappa squared. So that would be z of this conformal field theory on the torus. Okay? So that's a little part. I won't have time to explain it in detail, but that's a little part of the RCFT Chern-Simons correspondence. Another part here is that this formula here is essentially the Sugawara construction, which says that the stress energy tensor in this theory is minus a half d phi squared in this case. Okay. Now we are ready to go to higher genus. And I'm going to try and keep that brief. So, because it's quite a long story if I do it properly. But let me just indicate some of the ingredients. Okay, so now we're going to generalize this to sigma 2, which is a compact surface of genus bigger than 1. And so again, in Kähler quantization, we choose a complex structure on that Riemann surface. So we know what, say, the 1,0 differential forms are. And we use that to define a complex structure on the moduli space of flat connections. So we choose a complex structure on sigma 2, which is now higher genus, and genus bigger than 1. And that implies a complex structure on M flat, which I remind you can be written as this higher dimensional torus. So this is a 2G dimensional torus. Remember, these are flat gauge field. Can be written as F equals dA. A is a closed one form. And we're identifying A, remember, with A plus omega. We're under the large gauge transformations. That's the division by the lattice here. Okay, so how do we put a complex structure on this torus? Well, we declare that the holomorphic, the 1,0 tangent bundle, is just isomorphic to the 0,1 part of sigma 2. So if I have this higher genus surface and I choose a homology basis of A and B cycles, then I have a dual basis of 1 forms, real 1 forms, and then the 1,0 forms are going to be written this way, where tau ij is a G by G complex symmetric matrix with the imaginary part of tau that's now a matrix, but as a matrix it's positive definite. The space of such taus is called the Siegel upper half plane. Okay, so now there's a long story about how you take this torus, which now has a complex structure. It had a symplectic structure, so remember that if we have complex and we have symplectic and we have a metric, any two of the three give the third, and that gives you a Kähler manifold. Okay, so we now have this Kähler torus, and the quantization again goes in a very similar way. So there exists a special line bundle over M flat and J, a theta line bundle, and our states, where am I going to put it? I shouldn't have erased that. Our states are going to be holomorphic sections of the 2 kappath power over M flat and J, and a basis of those sections is going to be these higher genus level kappa theta functions divided by the determinant of the d-bar operator. So this is only a, and I put in quotes, function of tau. Okay, I'll talk about that in a second. First of all, what are these higher genus theta functions? Fortunately, I have not erased this. That's easy to say. We now have S is over a lattice. Here we have S sub I, mu sub I better put upper I's, tau ij, S upper J plus mu upper J over 2 kappa. Now you see why you want the imaginary part of this matrix tau ij to be positive definite, and then this is a function of z, where z is in C to the G. And now we have an analogous statement here. Theta mu kappa only depends on mu, which is in z to the G, 2 kappa z to the G. So in particular, this is a natural basis for a 2 kappa to the G dimensional space. And we have the same picture where we have this over the moduli space of complex structures on sigma 2, and we have to tensor with something called the determinant line bundle. So I'm not sure how Yuji Tachikawa is going to talk about anomalies, but a very important aspect in the theory of anomalies are what are called determinant line bundles. And if you try and take a determinant of an infinite dimensional operator that goes between two different Hilbert spaces, there's no natural definition of the determinant as a function. What you have to do is you have to interpret it as a section of a line bundle. So again, the mathematical fact that goes into here is the fact that if you take the determinant prime of dd bar divided by something like the integral of square root of g, the integral of the determinant of a basis of holomorphic 1,0 forms, this is equal to e to the minus k for the determinant line bundle times this holomorphic section, 4th power. Alrighty. And the same story is true. These again these are now the conformal blocks. These are the conformal blocks for the RCFT I wrote over there when I calculate the genus G partition function. All right, so now we're ready to move on to number 3. Let's talk about the Wilson operator approach. So let's talk about the operator algebra approach. Are there any questions about the Kähler quantization of the Hilbert space of states? No. Okay. So here we're going to quantize on A. First on A, space of all gauge potentials. And so now our gauge fields become operators. And this is the commutation relation. And so now let's take a loop, gamma, inside sigma 2. So for what? Yeah. So here's sigma 2, and so now I take some. Let me use some colored chalk, and so now I take some closed loop. Like that. So this is gamma, closed loop. And now the Wilson lines become operators. This is for representation n is an integer, that representation of u1. So this is just the following operator, in, the integral of a hat over gamma. Well, we might as well just call this w hat of n times gamma. Okay, and now you have this very simple commutation relation of these operators. And so now you can use the Baker-Campbell-Hausdorff theorem to show that w hat of gamma 1 times w hat of gamma 2 is equal to e to the I pi over 2 kappa I of gamma 1 gamma 2 times w hat of gamma 1 plus gamma 2. Where what is this capital I? Well, if I have two curves, gamma 1 and another curve on my surface, gamma 2, what I do is I sum over the intersections, assume transverse, of the local intersection number, which I defined previously. Let me remind you that we use the blackboard orientation. And so now if we have a crossing that looks like this, then iota equals +1. And if we have a crossing with the orientations like this, then iota equals -1. And so this, so why do we have this sum over the intersections? Because when you do the Baker-Campbell-Hausdorff formula, when you try and multiply these two operators, you're going to have the commutator, right? And the commutator, say, has a delta function. So it's only going to get contributions when you try and compute that commutator from the intersections. Okay. And if you're careful about the contribution, you'll find the local intersection number. All right, so now we observe the following. These operators only, w hat of gamma, only depend on gamma in the first homology once I impose the flatness of the gauge field. And so this I of gamma 1, gamma 2, I'll write this as gamma 1 inner product gamma 2. This is a antisymmetric z-valued product. And in fact, it's a symplectic product on the lattice. So what we've got here as an operator algebra is an example of what's called the non-commutative torus, or the irrational rotation algebra. So quite generally, if gamma is a symplectic lattice, then we can make an algebra, technically a C-star algebra, as follows. for every element gamma in the lattice, we have an operator x gamma. X gamma star is x minus gamma, and x gamma 1, x gamma 2 is q to the 1/2 times the inner product of gamma 1, gamma 2, x gamma 1 plus gamma 2. And this is an algebra that you find all over the place in physics. You find it in non-commutative geometry. You find it in the Hofstadter butterfly. Does everybody know what the Hofstadter butterfly is? Does anybody know what the Hofstadter butterfly is? One person. Well, if you want to see something way cool, look up the Hofstadter butterfly. It's the spectrum of the Schrödinger operator for an electron confined to 2 dimensions in the presence of a magnetic field and a periodic potential.
Fractal, right? It's a fractal, right? The spectrum.
Yes, it's very cool. So anyway, this non-commutative torus algebra or irrational rotation algebra shows up all the time. Now, this is defined for any complex number q. I'll call it AQ. If q is a root of unity, suddenly, you see, if I start taking x gammas to the nth power, they're going to start commuting. And so there's a huge center. There's an infinite dimensional center. This is an infinite dimensional algebra in general. But it has a huge center. So for us, the w hat of gammas to the 2 kappa are central. And so we could just put them all to be 1. And if we do that, what we get is, so AQ mod the center is equal to the group algebra of a finite Heisenberg algebra. Finite Heisenberg group, excuse me. What is that finite Heisenberg group? Well, we just take H1 of sigma 2, but now with coefficients in z mod 2 kappa z. So this, again, is what's called a symplectic abelian group. It has a symplectic form, which we can just take to be the intersection of gamma 1, gamma 2, modulo 2 kappa. So whenever you have a symplectic abelian group, you always automatically have a central extension called the Heisenberg group. So this is some finite group. And this is the group we should be representing on the space of states. So we want to represent this group on the space of states. Now, all Heisenberg groups have a unique representation, unitary representation, up to isomorphism. So all Heisenberg groups, and you learn that in basic quantum mechanics, but it extends to any Heisenberg group. All Heisenberg groups have a unique, up to isomorphism, unitary irrep, where the extension acts as a C number in the normal way. Just acts by multiplication. So what do? You have to choose coordinates and momenta. So what do we do here? We take our finite Heisenberg group and we write it as a sum of 2 subgroups which are maximal Lagrangian. So that's equivalent to choosing a set of A cycles on the Riemann surface and B cycles, okay? And then what's the Hilbert space? The Hilbert space H, the Hilbert space is L2 functions on the space of A cycles, on the maximal Lagrangian space. Now this is just a finite group in this case. This is Z mod 2 kappa Z to the gth power. And now we can write down the explicit representation of the Wilson operators. it's going to be W hat of gamma on a wave function. Well, its value on some gamma naught in here is just translation when gamma is in LA. And W hat of gamma dot psi evaluated on gamma naught is e to the 2 pi I gamma inner product gamma naught over 2 kappa psi of gamma naught. So just as in usual quantum mechanics, where momentum and position act either by translation or multiplication, here the A cycles are acting, the A cycle Wilson operators are acting by translation, and here the B cycle Wilson lines are acting by multiplication, and then using this operator algebra, you can calculate the action of any other Wilson line. So we have once again obtained a 2 kappa to the G dimensional space, and moreover, we know that there has to be, these Wilson lines have to act in this way on the theta functions. Okay, so now I'd like to talk about the modular group. Okay, so we've got here a topological field theory, and because we've got a topological field theory, the diffeomorphism group has to act on the space of states. So now we're here. So the so diff, and it has to be orientation preserving diffeomorphisms because we need an orientation in the theory. Diff plus should act on H of sigma 2, at least projectively, because that's all the quantum mechanics will guarantee for you. Now, because we're in a topological field theory, the diffeomorphisms, which are so-called topologically trivial or isotopic to the identity, form a normal subgroup of the diffeomorphism group. So what does this mean, isotopic to the identity? Well, you can give the diffeomorphism group a topology, and then it's those that can be continuously contracted to the identity. Another way of saying it is that if I have my surface and I look at some gamma, then we say that F is isotopic to F prime if I can deform F of gamma to F prime of gamma for all closed curves gamma. Okay. Now, because this is a normal subgroup, I can take the quotient, and that defines a group with many names. So one name is the modular group. Another name is the mapping class group. And another name is the Teichmuller group. Okay, so let me tell you some facts about this gamma G, the mapping class group. So gamma G acts on H1 of sigma 2z symplectically. You see, if I have a diffeomorphism and I have a flat gauge field, I can map it to A tilde equals F star A. Okay? And the intersection form in terms of the flat gauge fields is just the intersection, is just the integral of A1 wedge A2, and F is a diffeomorphism, so that will be preserved. So I have this symplectic action, and I'll come back to that in a second. So that's one fact. Another fact is that gamma sub G is generated by what are called Dane twists around closed curves. So what's a Dane twist? So supposing I have a surface like this, and I take a closed curve, and some colored chalk would be very useful here. And so what I do is I cut out an annular region around that closed curve. So locally it looks like this. So I just cut this out. And then what I do is I do the following. I hold the inner boundary fixed, and then I take the outer boundary and I rotate it around by 2 pi so that it comes back to itself. And then I glue it back in so that if I started before the Dane twist with a curve like this, then after the Dane twist, so this point doesn't move, but this point has rotated around 2 pi, so this is going to go around like that. Okay? So for example, let me do it for genus 1. For example, if this is the A cycle, and now I look at a B cycle like this, and I do a Dane twist around A, I'll get a torus where the B cycle now turns into a curve that looks like that. So that's the Dane twist around A applied to B. Okay. So those things are the things that generate the non-trivial diffeomorphisms of the surface of the mapping class group. So that's the second thing I wanted to say. The third thing I wanted to say is that not all of gamma G acts effectively on M flat. And why not? Well, you see, if I have a genus 2 curve here, so remember we had homology cycles, and we were interested in their intersections. Imagine doing a Dane twist around this curve here, a separating curve. It wouldn't touch those. It wouldn't touch the A and B cycles. So it would act trivially. So there's a normal subgroup also of the mapping class group, and it turns out that the quotient is isomorphic to SP2GZ, which are the symplectic automorphisms of M flat. All right, so that's what we should be trying to represent on our Hilbert space of states. So let's try that at genus 1. Okay, so let's try this at genus 1. Okay, so there are no separating curves, so the NG, which is called the Torelli group, acts trivially. So what are our diffeomorphisms? They simply look like this. It goes to, let's say, delta sigma 1 plus beta sigma 2, gamma sigma 1 plus alpha sigma 2, where alpha, beta, gamma, delta is in SP2Z, which is identically the same as SL2Z. And I chose this so that tau tilde is alpha tau plus beta over gamma tau plus delta. Let's see it act on our gauge fields. So A tilde is F star of A. That's F star of little a1 d sigma 1 plus little a2 d sigma 2. And now I write that in terms of my complex coordinates. So I'll leave it as an exercise to show that Z tilde, which is A2 tilde minus tau tilde A1 tilde divided by 2 pi, is just Z over gamma tau plus delta. Okay, so that's how the modular group is acting on the flat gauge fields. Remember, Z is our holomorphic coordinate on the flat gauge fields. Now, SL2Z has two generators, S and T, and I'll choose S to be 0, -1, 1, 0, and t to be 1, 1, 0, 1. Now, people are always disagreeing about the sign of the choice of S. And when you're acting on tau, it doesn't matter. Only PSL2Z acts. But when you're acting on the flat gauge fields, the sign of S matters. And this is a choice I made. I'm not sure it's the most brilliant choice, but it's a choice I made. So the relations are st cubed equals s squared is minus 1. OK. So now we act on the quantum states. And so that there's well-defined transformation laws for theta functions and eta functions. And I'll just tell you what happens. So rho of t, what it does is it takes psi mu kappa, goes to e to the 2 pi I mu squared over 4 kappa minus 1 over 24 times psi of mu kappa. And rho of s, rho is the representation on the space of physical states, is 1 over the square root of 2 kappa. It's a finite Fourier transform, e to the 2 pi I mu nu over 2 kappa, psi of nu kappa. OK, so now let's check the relations. OK, so first of all, what about s squared equals minus 1? Well, that works beautifully because you all know that the Fourier transform is order 4, not 2, right? The Fourier transform is not order 2. The Fourier transform is order 4. Takes f of x to f of minus x. So rho of s squared is indeed minus 1. It takes z in tau, goes to minus z in tau, and indeed theta of mu kappa of minus z in tau is theta of minus mu and kappa of z and tau, which is what you'd get by squaring the Fourier transform. OK, question? All right, now the harder one is st cubed, which is best written as sts equals t inverse s inverse t inverse. So t is diagonal, s is a finite Fourier transform. So this boils down, because of this quadratic nature of the t action here, to a kind of a finite Gauss sum. So the fact you need is the following sum. E to the 2 pi I nu squared over 2 kappa, which is an eighth root of unity. And now you check, this is an exercise, rho of s, rho of t cubed is e to the minus 2 pi I over 6, rho of s squared. And so indeed, the modular group acts projectively on our space of states, as we were threatening. All right, so now let's move on. That's all I'm going to say about the space of physical states. And now I want to talk about going back to 3 dimensions, but still sticking with the U1 theory. I want to talk about correlation functions of Wilson line operators, or Wilson line defects more properly. OK, so let's do that. And in principle, this could be done in any 3 manifold, but we'll take the simplest case. So we want to look at loop correlators in R3. OK, so the product over alpha of the Wilson line defect. So this is going to be with charge R alpha around loops alpha. So what is this? This is the integral over a mod g dA of the exponential of I kappa over 2 pi integral of a dA plus I times the sum over alpha. We're just integrating over R3 now. R alpha times the integral around gamma alpha of A. OK, and so I've got these loops, which might be linked and might be knotted. Who knows? So a few remarks. One is that this is the unnormalized correlator. So in topological field theory, usually in field theory, you have no respect for the overall normalization of the measure in the path integral. But in topological field theory, you can't do that because, after all, the path integral is supposed to be counting invariants, like Donaldson invariants, or counting Euler characters, or counting something, okay? So, for example, in topological field theory, it's always true that S1 times spatial D manifold is equal to the dimension of MD minus 1. Okay? So, sorry, the Hilbert space on MD minus 1. So the normalization of the path integral in topological field theory really matters. Okay, we'll come back to that normalization if there's time. The second thing is that this is Gaussian. As I said in the first lecture, there's no excuse. So you do the integral. You just do stationary phase here, solve the equations of motion, and this becomes n times the exponential, the sum over alpha and beta, of 2 pi I over 4 kappa r alpha r beta, where L of gamma alpha gamma beta is the, this is called the Gaussian linking number. It's a topological invariant. It can be defined in many ways. It's symmetric. The way it comes out in this path integral is that it's an integral of a certain 2 form over gamma 1 times gamma 2 of omega of x1 minus x2, where omega of x is the following 2 form, basically your Green's function, epsilon ijk xi dxj dxk over x cubed. Okay? So, so notice there's one problem here, right? Does anybody notice it? Pardon? Thank you. Yeah. Right. So, you know, what Clay said is that he's pointing out that when alpha equals beta, we have a problem. So we have gamma, gamma alpha, gamma beta. Gamma alpha is ill-defined. Incidentally, this linking number appears already in Maxwell's book on electricity and magnetism. So Maxwell asked the following question. Supposing I have current along some loop, current I along some loop gamma 1, and I have another loop gamma 2, and you could ask, what is the work done by the magnetic field on a magnetic monopole that's transported around gamma 2? And the answer is I times the linking number. And from that description, it's not obvious that this is a topological invariant or symmetric, but it is. It's a symmetric topological invariant. So, okay, so what are we going to do about this? It's not obvious. It's magnetic monopoles. Hello? Oh, hi, Nadi. Yeah. The students here are really good. Yeah. I covered the Hilbert space on the surface. I showed that the modular group is projectively realized. No, I haven't gotten to the framing anomaly yet. I'm just about to get. Just the U1 case. No, I'm not going to get to spin theories. Yeah, nobody asked. You'll have to do that. Okay, ciao. So this is ill-defined. And so what we do is we use point splitting. So we take gamma alpha and we deform it to gamma alpha tilde. And the way we do this is we choose a non-zero section of the normal bundle. And you should think of it as a small, infinitesimally small, non-zero section of the normal bundle. So I'll denote that by f, and f is equivalent to f prime if they are continuously deformed into each other through non-zero sections. You're not allowed to have a zero section. Okay, so let's call this deformed thing gamma alpha plus f. And we'll define this to be the linking number of gamma plus f. And so it depends on a choice of framing. Now notice that you can change framing, right? So you could spin this vector around a little bit. So the framings are what are called a z-torsor. I'll say what that is in a second. So what we discover here, actually we get a lot of lessons associated with this. So quantum mechanically, our Wilson loop gets an extra degree of freedom. So quantum mechanically, what we find is that we don't have W of R gamma, we have W of R gamma F, where F is a framing. Okay? So what the Wilson operators are really describing are, we have ribbons. Okay? So the Wilson line defects are really associated with ribbons. Now, as I was just saying, the framings form a z-torsor. Does everybody know what a torsor is? Does anybody know what a torsor is? One person. Okay. Now look, this is language you should know. If G acts on a set X, then if it acts transitively, what does that mean? You can get from any one point on X to every other point on X with some G. Okay? If it's fixed point free, that means that no element of G other than the identity fixes any X. Okay? So X is a G-torsor if the G action is transitive and free. So it's like a copy of G, but there's no choice of the identity. So the framings are like that. You get from one framing to any other framing by spinning it around. Okay, so we can take this ribbon and we can spin it around. That's spinning around the framing. And we can study how the Wilson line responds to this spinning of the framing, and that defines, naturally enough, the spin of the line defect. So we have W of R gamma F plus N, N is an integer, is the exponential of 2 pi I R squared over 4 kappa to the nth power W of R gamma F. Okay? And this is called the spin. And in the RCFT correspondence, this is the conformal dimension modulo 1 of a corresponding primary field with respect to the relevant chiral algebra. Okay, now we also see that the correlator is periodic in R. Namely, if we shift the R alphas, goes to R alpha plus 2 kappa times L alpha are integers, then the correlator is unchanged. You could just check that explicitly from the answer. So that means that W of R plus 2 kappa gamma F is W of R gamma F, and that implies that there's only a 2 kappa dimensional space of Wilson line defects, and that should remind you of the space of states on the torus. Before I go there, I want to make one last remark that we can get from this correlation function, and that is if we have two line defects linking like this with charges R1 and R2, and they don't link anything else, then you see that's just equivalent to a C number that's equal to e to the 2 pi I R1 R2 over 2 kappa, which, look at that, is the S matrix for the modular transformation. And this is a general result in three-dimensional Chern-Simons theory, that the amplitude for having two linked line defects with different different representations is the S matrix amplitude. This is part of the beginning of the proof of something called the Frelinde formula. Okay, so I have a few minutes, so I want to close by explaining why it is that these Wilson lines form a 2 kappa dimensional space, which is isomorphic to the space of states on the torus. Okay, so again, in general, in field theory, if I have a manifold which is a boundary of another manifold, and I have some fields on W, let's say we have fields phi here, well, we'll have to put some boundary conditions on those fields. Let's just call it phi sub delta. Okay, so we can define a wave function, a state, in the Hilbert space of M. So this is psi is in the Hilbert space of M, which is defined by the path integral over all phi's. We're integrating over all phi's that satisfy the boundary condition phi boundary, e to the I s. Okay, that's just a conceptual thing. So let's apply that idea to the solid torus. Okay, so we have the solid torus, which is the disk times the circle. And now what we're, or if you wish, we can draw it like this, and we can fill it in. And now what we're going to do is we'll insert I think I'll talk to that later. Okay. We'll insert a W of R gamma F at the origin times S1. Okay, so we're going to insert our Wilson line at the center of this solid torus like this. Okay, so now that's going to creates a state which I'll call psi sub r in the Hilbert space of the torus, and now you know everything about the Hilbert space of the torus, right? So let's try and understand something about the states that get created here. Well, let's think about those Wilson operators on the space of states. And we'll think about the Wilson operators around the A and the B cycles. So here's the A cycle in blue. And this is the B cycle. This is the A cycle. Okay, so now imagine acting with W hat of gamma sub B. I guess I'm calling it gamma sub B. And this is gamma sub A. Imagine acting with W hat of gamma sub B on psi sub R. Okay, so that means we're integrating e to the I integral of A hat around gamma B. But now, this is topological field theory. So I could take that line and I can let it sink into the center of the solid torus, right? And I can let it merge with the Wilson line at the beginning, at the center, and so this is just psi r plus 1. And similarly, with gamma A, I can take this Wilson line around here, and I can let it sink into the center of the solid torus. And now you see it's linking the Wilson line at the center. And we have this rule here. And so we get, lo and behold, our representation of our finite Heisenberg group. Okay, good. Now, there's a bit of an embarrassment. Oh yeah, sorry, not yet. Not yet embarrassed. Okay, now let's ask, how does the modular group act? Okay, so let's first look at T, okay, which is the Dane twist around A. So what's that going to do? So we do our Dane twist around A, so we're going to do twisting around here. Now in here, somebody should have objected. I need to choose a framing, and I'm going to choose this standard framing. But if I choose that standard framing, which is pointing out radially, and I do a Dane twist, it's going to wrap around one time after the Dane twist. So F is going to go to F plus 1. Kudos to whoever got this new chalk. And so we're going to get a factor of e to the 2 pi I r squared over 2 kappa. Because that's how, from this formula over here, that's what happens when we shift framing by 1. So here's the embarrassment. What about the exponential of minus 2 pi I over 24? Well, that's because we haven't talked about the normalization factor here. So real quick, I'm at the end of my time. The normalization factor, well, I'm going to write it for any 3 manifold, is this integral. Okay, and I don't have time to tell you about the Fadeev-Popov regularization and all of that. So let me just write the answer and talk about it a little bit. So what comes out of this is the square root of the determinant. But there is one very important conceptual point. So now I have to gauge fix. Okay? Now I have to gauge fix. And that means I need to introduce a metric. Okay, so if we're really honest about doing this path integral, we need to introduce a metric. And so if we choose, for example, Lorentz gauge, okay, we have to use the metric to define star of A. Okay, once you've done that, well, you've opened Pandora's box. You've had to introduce that metric into your topological field theory. So you have to worry, have you completely spoiled topological invariance? So that's the last thing I want to say. So now what you find is n is, okay, you do some one-loop determinants, and it turns out to be star d star, the Laplacian on 0 forms divided by the star d on omega 1 on the image of d dagger, absolute value, times the exponential of I pi over 2, the eta invariant of d, where d is an operator from the odd forms on M3 to the odd forms on M3, which is given by star d plus d star. Alrighty. So, a word about this. So first, the ratio of determinants. This is called racing or torsion. And there are supersymmetric cancellations exactly in the way that Clay was explaining. You see, remember he said that if you consider superquantum mechanics on a manifold, in this case a 3 manifold, then our Hilbert space of states is going to be something like this. Okay, and as described in my notes, we can split this up using Hodge theory, but that's exactly the way supersymmetry would tell you to split up the space. And there are cancellations between the eigenvalues of this operator and this operator, so that the result is indeed a topological invariant. But then we have this phase here. This phase comes from this operator. You get that from the Fadeev-Popov way of or BRST evaluation of the path integral. And this operator D is actually a Dirac operator in disguise. If you take spinors valued in the spinor bundle, so the tensor product of spinors with spinors goes like differential forms. And when you do that, the Dirac operator becomes star D plus D star. So here's a general fact about Dirac operators in odd dimensions. So if I have a Dirac operator on a spinor bundle coupled to some gauge bundle over an odd dimensional compact manifold, then you can define rigorously, I don't have time for it, but you can define rigorously something called the eta invariant of that Dirac operator, which is the sum of +1 over all the positive modes minus the sum of +1 over all the negative modes. So you see, in even dimensions, the Dirac operator has a spectrum. The Dirac operator has a spectrum which is symmetric around 0 because it anti-commutes with the analog of gamma 5. So in even dimensions, gamma 5, or its analog, will anti-commute with the Dirac operator, and so gamma 5 squares to 1, and so the spectrum is symmetric around 0. But in odd dimensions, there's no gamma 5, and so the spectrum of the Dirac operator can have what's called a spectral asymmetry. And so now, oh, I'm way over. Let me just, one more word to finish the thought, and then I'll be done. So there's a beautiful theorem that says, it's called the APS index theorem, that says that if I have an even dimensional manifold here and an odd dimensional manifold here, then there's a way of defining boundary conditions on the even dimensional Dirac operator on W, so that this index is equal to the integral over W2n plus 2 of a hat of the metric. These are the Weil representatives of the Chern classes, of the characteristic classes, and then we subtract eta plus the number of 0 modes over 2. Now, this is an integral of these characteristic classes over an open manifold, so it changes continuously. With metric and gauge field. But this is an integer, so that means that the variation of the eta invariant is given by the Chern-Simons, this variation. So the variation of the eta invariant is 2 times the variation of the Chern-Simons form for that characteristic class, which means you can cancel off the continuous variation with respect to metric by a local counterterm, namely the Chern-Simons form for the metric. What remains, so you have to add that as a counterterm to your three-dimensional topological field, to your three-dimensional theory in order to obtain a topological field theory, and then the result is what remains is topological. So thank you. I'm done.
We're a little over. Maybe one quick question.
Yeah, so we have studied the Hilbert space associated to it also easy to see that they are also orthonormal? Because that's
Yeah, same thing. So it comes down, that comes down to an easy calculation. Oh, sorry, the question was, I sort of justify the division by eta, the Dedekind eta function and the determinant of the d-bar operator by saying, well, okay, if I work up on the space of all gauge fields, I want to have some kind of normalization condition. And then the question was, well, what about orthonormality? Do we also have this formula for r not equal to s? And the answer is yes, it's rather easy. So if you integrate over the moduli space of flat connections, theta star r, theta s, that will be proportional to delta rs.
All right, well, let's save our questions for the break since we're over, and let's thank Greg again for his quick question. That representation of the modular group you were earlier was the Vey representation, right?
That's probably right, yeah.
And you were arguing that it acts projectively,
Yes.
but there was like a third root of unity that appears. But I thought it was an honest representation.
Well, I'm not sure it's exactly the Vey representation, which is a double cover. That's a representation of the metaplectic group.
Yeah. So okay, so it's not the Vey representation.
I guess
That's how
not.
the theta functions transform. So
Theta functions.
yeah.
But then there's this division by eta, which has a 1 over 24.
Okay, great. There we go.
So it's the 1 over 24 that's really getting you.
Yeah. Okay, thanks.
Could I ask a bunch of questions about APS index theorem?
Yeah.
So if you look at like a APS boundary condition, it only looks like some cubosymmetry condition. So if I use some like calibrated M5 brains or D brains, could I just naively use APS band, say that I'm using APS boundary conditions so that I could possibly use some APS index theorems or something like that?
Well, yeah, sure.